afternoon, everybody. Next week, we're going to listen to Jason Schenkel talk about functional programming. And if there's anyone who can make it, spice it up and make it exciting, it's Jason. So if you're interested in functional programming, attend next week's colloquium. Today I have the pleasure of introducing you to Dr. Hao Yue from San Francisco State, our sister institution, who's going to explain to us what is an RFID network. So let's welcome him.
Thank you. Thank you very much. First, thank Professor Levine for the nice introduction. Okay. Good morning, everyone. My name is Hao Yue, and I'm very glad to come here and give a talk about my research on RFID networks. Okay. So first, I want to introduce me a little bit. Okay. So currently, I'm an assistant professor in the computer science department at San Francisco State University. I got my PhD last summer from University of Florida. And after that, I joined SFSU. Okay? My research focused on computer networks and network security, especially the networking and the security problems in Internet of Things. I'm not sure if you have heard of Internet of Things before, but Internet of Things is like currently Internet mainly information infrastructure which provides service for human beings, so we can exchange information over Internet. But in the future, we expect that more and more physical objects, or we call them things, like your watch, your water cup, and your shoes. A lot of things can also be connected to Internet and talk with the outside world. Okay? So then we call the new generation of Internet of Things. So my research focuses on network and security problems in the context of Internet of Things. So this is my university, and this is our one of our main buildings is a new library. Okay, so here is the outline of my today's talk. First, I will give a brief introduction about RFID networks, so everyone here can have a background about RFID system. And then I will talk about our work. It's like we developed a novel protocol for information collection in RFID networks. After that, I will show some simulation results, compare the performance of our method with some other existing method, and that is a conclusion part. Okay, so what is an RFID network? What is an RFID network? RFID network is very simple. A typical RFID network consists of two parts. Okay, so readers and tags. Readers and tags. In RFID networks, each tag has a unique ID, and usually we can attach the tag to the product or object. Then the tag can store information about the object. For example, if you attach the tag to some product, you can save the information like the name of the product, where is a product produced, and when is a product expired. Some information like that. You can save a lot of information into the RFID tags. And later, you can use a reader, this one. Okay? Here, this one is a handheld reader. It's a mobile reader. In practice, we can also have the static reader. So you can use reader. You can use readers to wirelessly communicate with those tags and collect the information from those tags. So you can get a lot of knowledge from the objects or product in your system. Okay. So this is a typical RFID networks. Okay. Very, very simple. And so here I want to emphasize that. So the the tags, they will not communicate with each other. In this system, only the reader, the tags will only talk to readers. Okay. RFID networks was first invented actually to replace the barcode system in the supermarket. Okay. So, but nowadays RFID networks have already been used in a lot of areas in our daily life. For example, like the transportation, like energy, healthcare, and the warehouse management. A lot of areas, many interesting applications. So, for example, if you drive in California, I think you should be very familiar with this one, Fast Track, right? Fast Track. So here is one toll plaza and with Fast Track. Actually, Fast Track use RFID techniques. Fast Track use RFID techniques. So in the toll station, okay, there is a reader installed in the toll station, someplace here. And then if you buy the Fast Track, and you will receive a small device, right? Small device, and you put the device on your car. Actually, that device is a tag. It saves your information like your name, your plate number, and your credit card information into that small device. It's a tag. So every time when you drive a car and go through the toll station, okay, the reader installed in the toll station wirelessly communicate with the tag attached to your car, and can get your name, get your plate number, get your credit card information. So they can charge you electrically. So you don't need to stop, wait, and pay like you go through a normal lane in the toll station, right? So we know that in the rush hours, okay, if you don't have a fast track, you want to go to this normal lane, you may have to wait for a long time, and then you can go through the toll station, right? So fast track can help you and save you a lot of time, especially in the rush hours. This is one typical application of RFID networks. Okay. RFID networks can also be used in the supermarket to create so-called smart shelf. Smart shelf. So in the supermarket, we can put an RFID reader in the shelf and attach the tags to all the products on that shelf. Then the reader can periodically communicate with all the tags. So you can monitor, for example, if some product are run out, then you will know that, and you can have a automatically replenishment. Okay? Or if someone move the product from one shelf to another shelf by mistake, you can also know that. So you can send an alert, and the worker can come here and move it back. Okay? So in this case, we can save a lot of, if we use this smart shelf, okay, a lot of tasks can be automated. So we can save a lot of labor force and save a lot of money. Okay? Give you another example. So RFID, we can also add some small or say mini sensors to RFID tags. So the tag can also have some sensing capabilities to monitor the state of the product. For example, we can deploy those kind of sensor augmented RFID tags into a large-scale frozen food storage facility, okay, to monitor the temperature of the food. So in this application, we deploy the RFID system, and each tag can periodically monitor the temperature of the frozen food, collect the reading values, and then the reader can collect all the values to a server, for example, and the server can analyze those data. If some abnormal temperature reading is found, then the system can send an alert so the people can come and check the quality of the food. We can ensure food safety. Okay? Food safety is very important for us, for humans. Okay. the RFID networks have also been used in farmers, in the large farms. So the farmers use the network to track the animals like sheep, corn, and they can also monitor their temperature to prevent the some disease. Okay, so based on a big data report in 2011, okay, the total number of RFID tags sold globally around the world will be increased from 12 million in 2011 to 209 billion in 2021. Okay, this is a very, very huge number. So there is potentially there is a very huge market for RFID networks. Okay. Okay. So I have talked several examples, several applications of RFID networks. You can see that in those applications. Okay, so we always need to collect information or data from all the tags to the readers, right? So we have to ask the reader to collect the information from all those tags in the network. So information collection is a very fundamental and also very important function in RFID networks. So we have to develop the efficient protocols for information collection in RFID networks. Okay? However, this is not an easy task. So it is very challenging to design an efficient information collection protocol for RFID networks. Why? Why is that? Okay. There are three main reasons. The first one is, okay, in some applications, the time constraint for information collection is very tight. For example, let's go back to the application of the frozen food storage facility. Okay, so based on the law in U.S. About food safety, okay, in those large-scale food storage facility, it is required that you we have to collect the data in every 3 minutes to ensure a real-time monitoring. Okay, so you can see the time constraint in this application is very tight. You only have 3 minutes. But on the other hand, in RFID networks, usually there are hundreds of thousands of product or objects in your system. You have to collect the information from a huge number of tags. So the volume of the information you have to collect is very huge. Okay, so let's make the real-time information collection in RFID networks very, very challenging. Okay. In addition to those two reasons, the advantage of RFID network is that RFID tags is very cheap. Nowadays, we can spend only 5 cents to produce one RFID tag. So the cost for RFID tags is very cheap. This is also the reason why RFID networks nowadays have been widely used in many applications because of its low cost. But since the cost is very low, so the hardware of the RFID tag is very simple. It's very simple. The hardware is very simple. A lot of RFID tags are called passive tags. They even don't have the power source on the chip. Okay, so the hardware of RFID tags is very simple, so they are not able to run sophisticated operations. If you started computer networks before, you probably know that there have already been a lot of protocols developed in wireless sensor networks. Okay, however, we cannot directly borrow those protocols and apply them in RFID networks. Why? Because the RFID tags are not able to support those protocols. They are too sophisticated. Okay? So we have to develop new lightweight protocols for information collection in RFID networks. And in this work, actually, we developed two information collection protocols by using some lightweight data structures and techniques. Okay. Next, I will explain our protocols. Okay. First, I will formally define the information collection protocol we want to address. Okay, so we consider a typical RFID networks and focus on one reader. And this reader now wants to collect the information from all the tags in its communication range. Okay, so in this example, we can see that in the whole system, there are 10 tags, ID 1 to ID 10. And this reader now is going to collect the information from all the tags in its coverage region. So there are 3 tags in the coverage region, right? ID 1 to ID 3. Okay? And in my presentation, I will use the big U to represent the set of all the tags in the system. In this example, U is the set consisting of ID 1 to ID 10. And I will use the big S to represent the set of tags in the reader's coverage region. In other words, we call it target tags. So they are our targets. So in this example, S contains 3 tags, ID 1 to ID 3. Okay. And well, in RFID networks, in practice, most of the time, the reader is connected to a very powerful server through a high-speed communication network. Maybe it could be wireless network, it could be wired connection. Okay. So in here, we just simply consider that the reader itself has a very powerful computing capability and has enough storage. But in practice, the reader is well connected with a powerful server, so it can always send data to the server for storage and for computing. Okay? And again, so in the RFID networks, when reader and when readers and tags they want to talk to each other, they follow a protocol. It's called reader talks first protocol. So the tag are not able to initiate a conversation with a reader because most of the tags they don't have a power supply. So the reader have to first send some signal to the tags, and the tags will power their circuits by using the signal received from the reader, and then backscatter the signal and embed the information into the signal and send the signal back to the reader. So in the RFID networks, the reader initiates all the conversation by sending out some command, and then followed by the message sent from the tag to the reader. Okay? It is called reader talks first. Okay, so this is the model we consider here. And actually, this model is very general. It's a very general model. It can represent different types of RFID networks in practice. For example, we can use this model to represent a single reader RFID network. In this network, there's only one reader. So this reader covers all tags. In other words, all the tags in this network can communicate with the reader. Okay? We can see that in this scenario, actually, the U is equal to S, right? Because there's only one reader. Okay. We can also use this model to represent a multi-reader RFID network. So if the system is very large, and because the communication range of a reader is usually limited, so one reader cannot cover the whole area. In this case, we have to deploy multiple readers so they can collectively cover the whole area. In this case, one reader can only cover a subset of tags in the system, right? So in this scenario, S is a subset of U, right? S is just a subset of U, okay? in these two scenarios, the readers are static. Means after they are deployed, they cannot move. In practice, in some applications, we may have the mobile reader RFID networks. In those applications, a worker holds a mobile reader and move around in the system. When the worker reach to a certain point, reach to a certain location, the worker will stay here and use the reader to communicate with the nearby tags, collect the information from them, and then move to the next spot and repeat until the reader collects information from all the tags. Okay? We can see in this case, at each location, okay, the reader also, the reader still can only communicate with a subset of tags, right? Because the communication region is limited. Okay, so in this case, S is still a subset of U. Okay, different scenarios we can use our model to represent. So the model we consider here is a very general model. Then the problem we want to address is we want to design a information collection protocol for the reader to collect the information from all the tags in its coverage region. Okay, considering the time constraint, so we want the protocol to be time efficient, which means we want to collect the information with minimum running time. Okay, so we can meet the very tight time constraint in some applications. In addition to that, we also want to achieve information association by using our protocol. What's the meaning of information association? So we want to ensure that when the reader receives a piece of information from some tag, the reader is able to figure out the sender of the information. Okay, this is very important in some applications. For example, in the frozen food storage facility example, if you get an abnormal reading from some tag, you want to know the sender so that you can go and check the quality of the corresponding food, right? So this is also a very important design objective for our information collection protocol. So we want there are two design objectives: time efficiency and information association. Okay. Okay, and actually, there are two different scenarios for this information collection protocol. In some applications, before the reader wants to collect the information from the tags, the reader may have already known, okay, the set of target tags in its coverage region. In other words, the reader have already known all the target tags. In this case, we call the problem known target information collection problem. But in some other applications, this information may not be available to the reader. Or in other words, the reader doesn't know which tag is in its coverage region. In this case, we call the problem unknown target information collection problem. Next, I will talk about these two cases one by one. And I will begin with the first one, known target information collection problem, because this one is easier to solve than this one. Okay, so before I introduce my solution, first let's take a look at some simple, I call them warm-up solutions, okay, to get some insight on the information collection protocol design. Okay, so here are two warm-up solutions to this problem. Okay. First one is called Aloha-based protocol. Okay. If you started computer networks before, you should know that Aloha protocol actually is multiple access control protocols. Okay, so this protocol actually is developed based on the traditional Aloha protocol. In this protocol, there's no centralized coordination. So each tag will randomly select a time slot and then transmit its ID and the information to the reader. Okay? So they just randomly make a decision and then transmit their ID and the information to the reader. So since this is a wireless network, right? Since this is a wireless transmission. So in each time slot, if there is only one tag which transmits its ID and the information, then the reader can successfully receive that. In this case, the tag can stop because the reader has already successfully received your information. Okay? But if in a time slot there are 2 or more tags transmitting at the same time, I think this is a wireless transmission, so all their signals will be overlapped and then collide with each other. So at the reader side, the reader is not able to extract any useful information from the overlapped signal. Okay? In this case, the reader will inform those tags that, okay, your transmission is failed because of the transmission clearance. So in this case, those involved tags will try again in next round. And they will randomly choose another time slot and try, and hopefully this time the transmission is successful. Okay? So this protocol will run multiple rounds until all the tags successfully send their information to the reader. Okay. This is an Aloha-based protocol. Okay? Well, this protocol is very simple, but the performance of its performance is really bad. And there are 2 reasons, 2 drawbacks. The first one is, in this protocol, the tag has to transmit both its ID and the information to the reader. Okay? But actually, we only want the information. So the ID transmission is overhand in this protocol. But unfortunately, the ID transmission is very time-consuming in RFID networks. Based on the current standard, the tag ID usually has 96 bits. But in most of the applications, the message you want to send, the information you want to send, is maybe very short. For example, like 8 bits or 16 bits, right? So compared to the ID, the information is very short. So the ID transmission, the overhead for the ID transmission is very high in this protocol. So the efficiency is very low. Okay? This is one drawback. The other drawback is the very bad clearance in this protocol. Again, because there's no centralized coordination, right? So the probability that the transmission collide with others is very high. So there are a lot of time slots actually are wasted because of the transmission clearance. Okay, which also because of this reason, the protocol, the Aloha-based protocol, the performance of this protocol is very bad. Okay, so this is Aloha-based protocol. Another warm-up solution is called polling-based protocol. The idea of this protocol is very simple. So since now in the RFID networks, there's a reader, right? And the reader can communicate with all the tags. So let's make the reader as a coordinator to coordinate the behavior of all the tags in order to minimize the possible transmission clearance. Okay? So in this protocol, the reader performs a roll call. It's like the reader broadcasts the tag's ID one by one. Okay? Send the ID to all the tags. When a tag hears its own ID, then the tag will respond with its information. Okay? So it's like a roll call. I call your name, you answer my question, right? Okay. So in this case, we can see that there's no transmission clearance, right? Because after the reader broadcasts one ID, there's only one tag response. there's only one tag which responds. So there's no transmission clearance. But in the polling-based protocol, the reader still has to send the tag ID to all the tags. Again, ID transmission is very time-consuming, so the performance of this protocol is still not that good. Okay, all right. So those are the two warm-up solutions, and then we can get some insight on the information collection protocol design. Now we know that the drawbacks of those naive solutions is like, first one is time-consuming ID transmission, and another one is transmission clearance. So if we want to improve the performance, we have to first avoid ID transmissions and also minimize the transmission clearance so we can reduce the protocol running time. But this is not an easy task. Why? Because if we don't transmit any tag ID, then when the reader receives a piece of information, how does the reader figure out the sender of the information? In other words, how can we achieve the information association, right? And moreover, if we don't transmit any ID, then how to coordinate the tag's behavior to minimize the transmission clearance? Okay. So next, I will talk about our solution to solve those problems. Okay. So in our protocol, we use a very simple data structure. It's called a bit vector. Okay, to coordinate tags transmission, minimize the transmission clearance, and also we can use this bit vector to achieve information association. So in our protocol, first the reader will generate a bit vector, initialize all the bits to 0. Then the reader use a hash function to map all the tag IDs to the bit vector and set the value of the corresponding bits. So if there's only one tag ID mapping to the bit is set to 1. Otherwise, the bit is set to 0. Okay? So here's the example. After the reader generates the bit vector, the reader will broadcast the bit vector to all the tags in its coverage region. Then, after the tag receives this bit vector, the tag uses the same hash function, map its ID to the bit vector, and check the corresponding bit. Okay? So if the bit is equal to 1, for example, like the ID 2 is mapping to 1, then this tag is allowed to transmit its information back to the reader in the current round. Otherwise, if you are mapping to 0, then you are not allowed to transmit because of the potential transmission clearance with others. Okay? So in this case, only when you are mapping to 1, you are allowed to transmit. Okay, so after a tag is mapping to 1 and the tag knows that it can transmit, then it can also decide or say determine its transmission order by referring to this bit vector. Okay. Here, because each bit 1 in the bit vector actually corresponds to one tag that is allowed to transmit, right? So the tag can determine its order by counting the number of bit 1 appearing before its own bit in the bit vector, right? Here, this example is very simple. So ID 2 mapping to bit 1, and this bit 1 is the first bit 1 in the bit vector. So ID 2 will be the first tag to transmit its information back to the reader in the current round. If there's another tag who is mapping to the second bit in the bit vector, a second bit 1 in the bit vector, then this tag will be the second. This tag will be the second guy to transmit its information back to the reader, and so on and so forth. In this case, different tags are assigned to different time slots, so there's no transmission clearance. Okay? And at the reader side, when the reader receives a piece of information transmitted from some tag, since the reader and the tags they share the same bit vector, the reader can always use the same bit vector and figure out the sender of the information. For example, if this is a second piece of information received by the in this example, this is the first piece of information received by the reader. So the reader can go back to the bit vector, find the first bit 1, and then go back to find the corresponding tag ID. So it will know the sender of the information. Okay? So we can see in our solution, okay, we use a bit vector to avoid any ID transmission. So we don't transmit any tag ID in our solution. And we also remove all the possible transmission clearance. There's no transmission clearance, right? And the bit vector is much shorter than the tag ID. So we can significantly reduce the running time of the whole protocol. Okay? So I want to emphasize that this is just one run. So for those tags who are mapping to bit 0, they cannot transmit in this round. But in the next round, they will map to different bits, and hopefully they can transmit in the next round, and so on and so forth until all the tags submit their information to the reader. Okay? So this is our solution to the known target information collection problem, where the tag has already known all the reader has already known all the tags is covered reader. Okay? Any question here? Okay. So we just solved the known target information collection problem. But in practice, in some applications, the target tags may not be known to the reader before the information collection. For example, in the supermarket, right, the product may be moved by the workers or by the customers from time to time, or in the farmers, the animals, they will move around in the system by themselves, right? So in those applications, the distribution of the tags changes over time. In other words, when a reader wants to collect the information from its nearby tags, the reader may not know which tag are in its covered region. So in this case, we face a new problem. It's called unknown target information collection problem. Okay. Obviously, our previous solution cannot be directly applied here to solve this new problem. Because you don't know the target tags, you are not able to map the ID to a bit vector, right? So, but since our previous solution has several advantages, like we can avoid ID transmission, we can minimize the transmission clearance. So here we want to extend our previous solution to, or say, develop another protocol based on the previous solution to address this unknown target information collection protocols. Okay? But how to do that? How to do that? One straightforward solution is that, okay, before the reader use our previous protocol to collect the information from those unknown target tags, the reader first asks all those tags to send their ID to the reader. Right? After the reader receives all the ID, then the reader knows all the target tags. We can apply our previous solution. Okay? It's very straightforward, but the problem is, again, ID transmission is very time consuming. So this is not a good solution. Right? Okay. So our idea is like, we want to use some compact data structure, okay, so that we can embed all the tag IDs into this data structure, and then we ask tag to transmit this data structure to the reader, and we can reduce the communication time here. So we decide to use Bloom filter. Okay, we decide to use Bloom filter. We want to transmit a Bloom filter of the set of target tags from the tag to the reader. So we can reduce the running time of our protocol. But the problem is, in this scenario, it is very challenging to construct the Bloom filter. Why is that? Why is that? So the traditional method to construct a Bloom filter is like, okay, given a set X, in order to construct a Bloom filter based on X, we have to first initialize one bit vector for each element in the set. Here there are 3 elements, so we initiate 3 bit vector and set all the bits to 0. Okay? Then we map each element to the bit vector by using a set of hash functions. And we will set the value of the bits to 1. Okay? So we map each element to the bit vector and set the value of the corresponding bit to 1. So we have 3 bit vectors. After that, we sum up all the bit vectors. We can get a new bit vector, and this bit vector is actually the Bloom filter for the original set S. Here, pay attention that this summation is not, the traditional summation we use. Here, the summation is a bitwise summation, and the rule of the summation is like, if there's any operand equal to 1, then the final result is 1. Only when all the operands are 0, the result is 0. Okay? So this is actually very similar to the OR operation. Okay? So this is the special summation operation. Okay? Only when all operands are equal to 0, the final result is 0. And this is the Bloom filter. Okay. If we want to use this method to construct a Bloom filter, this is the traditional way to construct a Bloom filter. If we want to use this method, here's to solve our problem. Okay, there is a big challenge here. If we want to use this method, first we have to know X, so that you can, construct those bit vectors for each element, and then sum them up, right? But the problem is, in our problem, we are facing the unknown target information collection problem, which means we don't know those targets. We don't know X. If we don't know X, we cannot use this method because we don't know the elements, right? So this method doesn't work. We have to develop a new method to construct the Bloom filter. So in our work, we develop a new method to construct a Bloom filter. We call it Bloom filter in R. Okay? So next I will explain that. So in our protocol, first, all the target tags will initiate a bit vector by themselves. Okay? Each tag initiates 1 bit vector and set all the bits to 0. After that, they use the same set of hash function, map its ID to the bit vector, and set the value of the corresponding bits to 1. After that, all the target tags transmit their bit vector to the reader simultaneously. Okay, and those are the physical signals for those bit vectors. In the physical layer, each bit 0 corresponds to an idle carrier, and each bit 1 corresponds to a busy carrier. Okay, so those physical signals will overlap with each other during transmission because this is wireless transmission. So at the reader side, the reader will receive an aggregated signal like this one. Okay? After the reader receives the signal, the reader can decode the physical signal and extract or say reconstruct a bit vector from the signal. The rule is if the channel is idle, then the bit is 0. If the channel is busy, the bit is 1. Okay? After the reader reconstructs the bit vector, And it turns out that this bit vector is equal to the Bloom filter we construct by using the traditional method. They are equal. So this is a Bloom filter for this set S. Okay? So the Y side, okay? Why can we construct a Bloom filter without knowing the set S? The magic here is like when those physical signals they overlap with each other, the rule is similar to the rule here. We add up those bit vectors. But the difference is that we do the summation here in the physical layer. And then we extract the bit vector from the physical signal. Okay? So, question.
Tell the difference between the three.
The difference between what?
The three. So you have an aggregated signal, right?
Yes.
You have, so basically a bitwise OR.
Yes.
How do you know which? You just assume that it's coming from all three signals, from all three IDs? How do you break out the IDs and the information on the IDs? Because how do you do the backwards OR to get back to the original ID?
ID. Okay, I will talk about that next slide.
Okay.
Okay. After you got the bit vector, right? Remember, the reader know the universal set U because usually this information is stored in the backend server. Okay, so the reader know all the IDs in the system. Then the reader will test every ID in the universal set U, and test them by using the Bloom filter. It just got. Okay, so the reader pick up one ID and use the same set of hash function, map the ID to the Bloom filter. Okay, if all the bits are equal to 1, like ID 1 here, okay, we believe that this is the target type. We put it to a new set. Okay, if after we map an ID to a bit vector, if any bit is equal to 0, then we say that, okay, this is not our target. We remove it. Okay. Here, there might be some ID that actually it is not in our target. It is not our target type. But with some probability that it also maps to all ones. In this case, we will also add the ID into the new set. So after we test everyone here, we can get a new set. This set will contain all our targets plus some mistakes, right? And we use S prime to represent this. Okay, so this S prime will contain all the IDs and some mistakes. This is called false positive mistakes. Okay, this is false positive mistakes for Bloom filter. After we got S prime, we can apply our previous protocol, collect the information from all these IDs. During this process, we can remove those mistakes because they are not in your coverage region. So when the reader wants to communicate with you, actually, because you are not in the region, you cannot reply. So we can finally remove all the mistakes. So we can successfully connect the information from all the tags. Okay? Okay, so I just talk about the protocols. Okay, I just talk about the protocols. And here are one question left is, well, here we use the Bloom filter, but how to decide the parameter of the Bloom filter, right? We want to choose some optimal parameters to minimize the execution time of our protocol. Here are some mathematical formulas. We try to find out the optimal length of the Bloom filter and the optimal number of hash functions we have to use to construct the Bloom filter. Okay, so based on those formulas, we can choose the optimal parameter then to minimize the execution time of our protocol. Okay, sometimes before you run the protocol, you don't know the number of the target tags. But if you want to calculate those parameters, you must know that parameter. If you don't know that, you can run some existing cardinality estimation protocols proposed by other researchers to first estimate the number of target tags. And there are a lot of existing work here, and you can just use them. Okay, so again, our protocol actually consists of 4 steps here. Okay, first cardinality estimation, and then parameter determination, Bloom filter in air, finally information transmission. in this work, we conduct simulations to evaluate the performance of our protocol. Okay, so all the simulation parameters are chosen from two commonly used standards. And here are some the parameters and the values. And in the protocol, we compare our protocol with different kinds of existing or the Warmup information collection protocols. And we found that the running time of our protocol is very small as compared to other protocols. And actually, we also set up this black line is actually represent a theoretical lower bound on the running time of any information collection protocols. We also observe that. Okay, so our protocol, the performance of our protocol is very close to the theoretical lower bound, which means our protocol, or the performance of our protocol is very good. Okay, so I don't have time, so I will not talk about those two figures in details. Okay, conclusion. So in this work, we studied the information collection protocol design for RFID systems. We also proposed a novel information collection protocol by using some lightweight data structures like the Bloom filter, hard functions, bit vectors to significantly reduce the running time of the information collection protocol. Okay, thank you very much, and I'm ready to answer any questions.